Hi, good morning, everyone, and welcome to this session of the CoE talk. Our presenter today will be Stephen James, who's in the computer science section of the School of Applied Maths here, but is generally involved in artificial intelligence, machine learning, and things that I'm not anyway an expert on. I would like, his title appears there, I would like Stephen to say before he spoke a little about the Google Award, which I think is a first in some sense. So I think the best person to do this is Stephen. Can you spend a couple of minutes with that?
Thanks for the introduction. Thanks everyone for attending my talk today. So I suppose before I get started, the Google kind of Fellowship Award is really designed for PhD students. Some years ago when I was doing my PhD, and it's really to support research in fields that Google are interested in. So this is things in computer science like operating systems, and machine learning is a big part of what Google does. And so in 2018, Google has had this award running for a long time. In 2018, they finally extended that to Africa. Previously, they supported students in the US, Asia, and Europe. And 2018 was the first time they had extended that award to students in Africa. And I was very fortunate to have won that award for machine learning. And subsequent to that, we've had a few students, also adverts, who have won that award. So that's just a bit about that background.
So you're the first in Africa, then?
Yes, in machine learning. Yeah. So there were, at the time in 2018, there were 4 of us who were awarded it. I was the only one in machine learning, and there were others dealing with like computer security and human-computer interaction and this stuff. Yeah. Anyways, so maybe I can get started with the talk today. So basically, what I want to talk about is a framework for working towards generally intelligent agents. So before I start on the actual presentation today, I just want to give you some background in terms of what artificial intelligence used to be. So AI kind of started in the 1950s, and the big idea there was to really say, we're going to write down the world as it exists, and we're going to write it down symbolically, which means that I can describe in exact detail what will happen when, say, a robot or something acting in that world does something. What is the outcome of that? And on the next slide, we'll see an example of what this looks like symbolically. But the idea was to say, okay, we're going to write down exactly how the world operates in great detail. And then what we're going to do is we're going to write a computer program, and we're going to do what's called planning. But basically, we're going to take that representation that a human has written down, and we're going to try to achieve some goal. We're going to try to say, how can I search through the space in order to achieve a goal? And there was a whole bunch of research in the space as to say, well, if I have such a representation that a human has given me, how do I do this planning quickly? So that was kind of the beginning of AI, and the thoughts there were that that was what was necessary to achieve generally intelligent agents. In particular, because the thinking was, well, humans reason symbolically about the world. When we do things like mathematics, we think about math symbolically. And so this is probably the way that you get your AI. So, there were some successes. So there was, in 1956, Newell, Simon, and Shaw had this computer program, for lack of a better word, called the logic theorist. And basically what it did was it took in mathematical axioms, and then it applied a bunch of rules, like inference and so on and so forth. And it built up further mathematical statements from those axioms, and it was useful for theorem proving. And so there were some interesting results where it solved it read out like 30 different equations in Bertrand Russell's Principia Mathematica. So these kind of symbolic methods were very useful for doing things like mathematical theorem proving. One of the main places where they operated in were these things called micro worlds, and these were like challenging but small puzzles. So as an example, you may have played a game called the Towers of Hanoi. And basically the game is something like this. You have, say, 3 pegs, and you have a bunch of discs, And the goal of this game is to move all the disks from, say, one peg to another peg. And the rules are basically that you can take off a disk and you can put it on another peg, but you can never put a larger disk on top of a smaller disk. It must always be that a smaller disk goes on top of a larger disk. So if we have a kind of intellectual puzzle like this, this is quite a challenging thing and quite a fun game for humans to play. And these are the kinds of problems that they were interested in. And so what the structure was to say, okay, let's take this problem, let's write down symbolically what this means. And below this diagram over here, you can see an example of what we mean by symbolic. So basically, this text description over here describes this entire world. And it basically says, we have the situation where there are a number of predicates, and predicates basically describe the state of the world. So you can have a disk, and there can be something on the disk or nothing on the disk. And we have this predicate that says smaller, which says, is one disk smaller than another disk? So a human has come in and written this down. And then there's this action called move, and move basically operates on a disk, and it says, well, I want to move a disk from, say, peg A to peg B, and this is what happens when I do that. And we write all of this down symbolically, and we'll get to the details in a bit about what each of these terms mean. But basically, a human comes in, takes this problem, writes it down, and then we give it to a computer program and we say, okay, we want to solve this problem where you move all the disks from, say, peg A to peg C. And this actually worked really well. So it solved some really hard problems. So here is an animation of it solving the problem for 3 disks, moving all the disks from A to C, maintaining that constraint of you can't put a larger disk on top of a smaller disk. And it can do this in basically no time, and it can also scale to much harder problems. So here's an example of it doing it for 8 disks. And this requires something like 250 steps. A human would take a really long time to do this. Again, because it has this symbolic representation that we've written down, the computer program, I ran this yesterday, it took 0.0 seconds to come up with the solution to this problem. Okay, so it was really good at solving these kinds of problems that were really challenging for humans. But it turns out that that was where the success ended, because when we try to take these approaches and put them in the real world, it doesn't really work. And one reason it doesn't work is it's great when you have a small self-contained problem and you're trying to solve that, but it requires an expert to come in and write everything down for you in order to solve it. So that requires a lot of work. And when your problems start becoming more and more complex, the amount of effort this requires of the human is just way too burdensome. And most of the time, actually, you can't do this. So if we consider more recent challenges like self-driving cars or having a robot, cooking, it's very hard to come in and write down a symbolic representation of what it means to drive a car, because there are so many outcomes that could happen. There are so many cases, there are so many edge cases. The world is noisy and continuous and just, high dimensional to deal with. And it's super unclear if you could ever write down a symbolic representation that describes such a world. So that was really kind of the fatal blow to these kinds of methods, but that it didn't work in the real world. Nonetheless, researchers persisted, and then there was this report by James Lighthill in 1973 that basically looked at the status of AI and came to the conclusion that the methods only worked in these small toy domains, and they were never ever looking to scale, and they were never going to scale to real world problems. And there was just too much hype around everything. And this report kind of led to the first AI winter, where people transitioned away from these symbolic methods to packing up methods. Okay, so that is the kind of background of where AI used to be. So it was great for planning in these small domains, but didn't scale to larger problems. Okay, so fast forward to 2022, we are now here, and all the rage these days is about machine learning. And machine learning is really saying we have a computer, there's a bunch of data, and we want to use that data to get the computer to do some task. And as we get more data in, the computer should become better at doing that task. So machine learning is all the rage. A lot of AI is really just machine learning. And we've made some great strides going down the machine learning paradigm. So for instance, a few months ago, DeepMind had a program called AlphaFold, which was for predicting how to fold protein structures in order to do drug discovery and things like that, winning some big competitions. That was all from machine learning. Again, DeepMind has alpha 0. And the idea here is you can learn how to play chess and checkers and shogi and all these two-player adversarial games without knowing anything about the games, just directly from playing millions and millions of games by itself, learning from that data, how to improve, and so on and so forth. And being quite general in terms of the kinds of two-player board games that it can play. And then there's work from OpenAI in things like DALL-E. So this is really about fusing multimodal inputs. So things like taking text, taking images, relating those two things. So the image on the left is generated by an AI, and I typed into the DALL-E program. I said, I want a picture of a corgi giving a presentation with a slideshow in the background, and the AI produced this image on the right here, just from that text prompt. And it can do this because it's trained on all the text data on the internet, trained on all the images on the internet, and it has these representations such that if I give it a new prompt, it can generate what it thinks the image corresponding to that prompt is.
Can you make me appear good looking?
Yes, of course. Well, that doesn't require much effort. So
am I that ugly?
No, just slight tweaks. So yeah. So anyway, so we've made a lot of progress in very narrow applications with machine learning, great successes in these various fields. Okay, but if we're talking about generally intelligent agents, the machine learning paradigm that really tackles that is what's known as reinforcement learning. And reinforcement learning, if you look at any kind of introductory slides or textbook, it has this little loop over here on the right-hand side. And basically the idea is as follows. There's some decision maker, which, if you're dealing just purely in the virtual world, might be a computer program. If you're dealing in the real world, it would be like a robot. But there is some thing that is making a decision, which we will call the agent. And that agent lives inside an environment. And basically what happens is the agent takes actions in the environment, just as we take actions in the real world. So the agent takes actions in the environment, and based on the actions of the agent, the environment changes in some way. And the environment changes, and so the agent observes that change. The agent observes, okay, I was at some initial state configuration of my environment. I take an action. Here is what happens next. This is what the environment now looks like. So the agent sees this observation, sees this change in the environment. And importantly here for reinforcement learning, the agent also receives some feedback from the environment in the form of a reward. And the reward is really an indication of whether the agent is doing the task that it was supposed to do or not. And this reward is like a scalar number that it gets back. So this is kind of the reinforcement learning setup, which is very broad. And way back when reinforcement learning was first introduced, this was the kind of framework, and people did various things. But as mathematicians are wont to do, we wanted like a general standard formalization of this loop, this kind of problem. And so everyone settled on this idea of a Markov decision process. So just very quickly, a Markov decision process is really described by this tuple over here. And it has the following 4 components. So it has what is called the states. The states are basically the configurations that your world could be in. And the states will very much depend on the kind of problem you're trying to solve. For instance, if you're playing chess, the state might just be the position on the chessboard. But if you're doing some other problem, it would be specific to that problem. The actions are basically the available choices that the agent has that it can execute in order to affect the world. So in this diagram over here, you can see we have some green states, S0, S1, S2, and a bunch of actions available at each of those states. So maybe at S0, the agent can take action A0 or can take action A1. Okay, so these are the first 2 components of the MVP. And then we have T, which is the transition function, and this basically says, well, the agent was at a state, it took some action. What is the next state that it finds itself in after taking that action? And basically, so for example, here it's still there. For example, if we're at state S0, we can take action A0, and the transition can be, stochastic, or it can be deterministic. In this diagram over here, if we are at state S0 and we take action A0, then with probability 0.3, the agent will find itself in state S2. And so the transition dynamics really describe how the world reacts when the agent takes an action in a given state, with what's the next state that the agent finds itself. Okay, and finally, we have the reward function. And the reward is really saying, well, if the agent was in a state and it takes an action and it transitions to a new state, what is the associated scalar feedback signal that it gets? So again, in this case, we would say, well, in state S0, if the agent takes action A0, then it transitions to S2 with probability 0.3, and it gets a reward of 0.1 in this case. Okay, so that is the kind of formalization of that agent environment interaction loop. And the aim really is to discover what is known as a policy. And a policy is just some kind of strategy that says, if I'm in some state, if the agent is in some state, what action does it take? And this policy can be deterministic or stochastic, but it's really just saying at each state that the agent could find itself at, what action should it take? And the overall aim is to learn what is known as an optimal policy. And the optimal policy basically is a policy that when you execute it, you get the maximum amount of return possible. So if we sum up all the rewards we get when executing the policy, we want the sum of all of those rewards to be as high as possible. And that's our optimal policy. That's what we want to learn. And we're going to learn this from interacting with the environment to learn. So the agent lives in the MVP, it takes some actions, it goes to new states, it gets some reward, and it must learn a policy based on this feedback. Now, I'm not going to get into it, but basically all of reinforcement learning is about given some MVP, put the agent in it, have it interact with the MVP, and use the data that it gets in order to learn an optimal policy. And there are hundreds and thousands of ways to do it. So that is the current kind of approach in machine learning for tackling the general AI problem. So one thing that's very clear if you read like an introductory textbook is that reinforcement learning was supposed to be about the idea of an agent interacting in its environment, taking decisions, and learning an optimal policy. And with this new formalization of an MVP, reinforcement learning really became about solving MVPs. So you can see even in the de facto textbook on reinforcement learning, it's all about MVPs. It's just saying we have an MVP and we want to solve it. It's not thinking about the bigger term picture. It's not thinking about general agents. It's just thinking about solving MVPs. It's kind of an assumption that is so pervasive in reinforcement learning that it's no longer an assumption. People don't bat an eyelid that we're making this assumption about Markov decision processing. But it is an assumption because if we want to get real world AI agents acting, alongside us in the real world, well, the world is real and the agent is a real thing. Both of these things are real. But this MVP is like an imagined abstract formalization that doesn't actually exist. And where did it come from? Well, if we look at something like two people playing a board game, what happens is some expert comes along and they say, well, your states should be the location of the pieces on the board, and the action should be, placing a piece at a particular location on the board. And so we've come basically full circle to the same situation where in the symbolic AI from back in the 50s, we had to have a human come in and write down everything in the world symbolically so that the agent could solve it. And here we have an MVP, but the human still has to come in and design this MVP, and they have to design it in such a way to achieve some task. So I know as a human, I want my agents to play chess. So then I can tell it, well, this is the states of the chessboard. These are the actions you can take. You can move pieces and so on and so forth. And so this is where we're at. But clearly, this isn't really going to work if we want generally intelligent agents. So again, just to recap, symbolic approaches, we told the agent how the world works. They used it to achieve some goal. It doesn't really work in anything outside of these toy problem domains. And in RL, we define the MVP, and this MVP might be very complex. In most cases it is, and might be very high dimensional and continuous and very nasty to work with. But the human is still defining the MVP, and then the agent interacts with it, learns a policy, and that's it. And this is more robust than, say, a symbolic method, but it still requires the human to come in and define this MVP. And clearly this isn't going to work for one, because we need humans in the loop. and we don't want to walk around with a robot all day telling it every task that it must solve, what the MVP for that task is. That's not going to work. And similarly, because necessarily each MVP is task specific because it defines the task to solve, well, an agent that can solve a given MVP can't really do anything else. If we have an agent that can optimally play chess, that's great if your goal is just to play chess. But if your goal is a general agent that can do many things, well, how is the chess playing agent going to drive a car or cook a meal? It can't, because you said that the states were chess positions and the actions were chess moves. So clearly it has no way of ever doing anything else besides playing chess. And so this approach in general is not going to work to get us generally intelligent agents. Okay, so what do we want? Well, the number one thing that we want is what we're going to assume is we have agents that are just like us. So if we're thinking about the human analog of a generally intelligent agent, well, I am a biological robot. I have sensors that I use to observe the world, my eyes, my ears, so on and so forth. So I have these sensors, I get in data, and I have actuators, which are things like making small muscle switches and things like that. So we have very complex sensory input, very complex action space, and we have one agent, right? I'm a single agent, but I can do many tasks. And one of the things that I can do is I can say, well, if I'm playing chess, it doesn't matter about the lighting conditions. It doesn't matter about the material that the chess pieces are made of or the size of the board. I can recognize that playing chess, all of these positions mean the same thing. They're all the same thing. And I know that when I'm playing chess, I observe the chess pieces through my eyes, but in my mind, I'm reasoning about chess at an abstract level. And when I take actions at that abstract level. So I can come in, sit down, look at the chessboard and play chess. And then similarly, if I walk into a kitchen, I understand that I'm in a kitchen. It doesn't matter the exact material that the kitchen is made of. I sense it through my eyes. I see these things. I have the same action space, but now I can go ahead and cook a meal or make breakfast or something like that. So what we want is a single agent that is very complex. It needs to be very complex because we need it to do very complex things. So the agent must be very complex, but it must also be able to say, I'll put it down in front of a task. It must know how to solve that task given this initial setup. So we want that. And one way of potentially getting to this is to say, if I put the agent in a new task, it must learn its own representation. So no longer must we say a human must come in and write down the symbols, or a human must come in and write down the MVP to define the task. No, we want to say the agent must come in, observe the world, and from those observations, come up with its own task-specific representation for solving it. And then given that it has learned that representation, then you can go off and apply any of these learning methods that people have been spending the last 50 years on. So that's what we would ideally like. And because we are basically saying we have an agent who makes observations of the world, we want to use that to learn a representation. Well, that sounds like a perfect job for machine learning. But it turns out, if we want to do this, maybe we need lots of data. Maybe we need so much data that it's just not feasible to ever do in any real context. And so potentially one way around this is to say, well, if I've learned a representation for one task, maybe when I see a new task, I don't have to learn from scratch. Maybe I can reuse parts of that knowledge in my new task to help speed things up. So as a very brief example, imagine I learn how to play chess. If I'm then put in front of another similar game like checkers, I don't have to relearn from scratch. I can maybe use the idea, I know something about that it's a two-player game. I understand that my opponent has pieces, I have pieces. I want to win, they want to win. These two things are mutually exclusive. We take turns. The pieces exist on individual squares and so on and so forth. The minor details are different between chess and checkers, but there's a lot that we can reuse between tasks that will hopefully speed up it. Okay. So question number one to ask then is, well, if we want to learn a representation to solve a task, what is the right representation? And the answer to this really is that it depends on the application. So for instance, doing things like playing chess, where it's a two-player game and you take turns, is a completely different thing from doing self-driving cars. Self-driving cars are all about like continuous control and reacting and so on and so forth, whereas games like chess are about planning and thinking deeply and slowly. The representations that we want really depend on what we're trying to achieve. And so I don't have a solution to the full thing, but what I want to do in the rest of this talk is focus on what is known as high-level planning. One reason I want to focus on this is because it turns out that current reinforcement learning techniques really struggle with this. So for instance, if we have this kind of video game over here, high-level planning says, well, if I want to get out of this first room that I'm in, the little man over there, the little agent has to jump over the gap, climb down the ladder, jump onto the rope, jump over, climb down the ladder, jump over the skull, go get the key, and then go all the way back up, and then go through one of the doors, top left or top right. And it turns out that this is a really hard problem because it requires a lot of planning into the future in order to work out how to get out of the room. And if you only get a reward once you get out of the room, well, then you have to take 10,000 actions in order to get a single scalar value. And so that's going to be a very hard signal to learn from. Okay, so high-level planning basically is what symbolic representations were invented for in the first place, right? And it's basically saying, we want a plan, we want a sequence of actions that achieve some goal. This plan can be really, really long. And the question is now not, okay, well, I'm going to write down a symbolic representation. How do we come up with a plan? It's first going to be about how do we learn a symbolic representation in the first place? How do we learn a suitable representation such that we can plan? And then a secondary point, which I mentioned earlier, is, well, it might require a lot of data. Can we reuse this in different contexts? Okay, and so this is an example from work we have done, where you can see a video game character kind of doing the same idea, where it has to go around, collect the key, open the lock, get the treasure, and then go back up to the top. And you can see in the top right corner, there's a count of the total actions. And this is something like 1,500 actions in order to achieve the goal of collecting the treasure and getting back to the top of the roof. And we can only do this because we are doing long-term planning. So this is just a spoiler for the kinds of things we can do that standard reinforcement learning approaches just really struggle with. Okay, so let's quickly go back to symbolic representations. This is from that initial slide, and we can really break down exactly what we're seeing here because these are the things we need to learn. Okay, so the first thing is really about the predicates. And the predicates describe the state of the world. And these predicates are kind of Boolean functions. You can think of them as that, and they're either true or false. And you can see here they're parameterized by X and Y, which are different objects. And so the predicates here describe the world symbolically. So for instance, you have clear, and it takes in a value of X. So we can say, okay, is a particular disk clear? Is there nothing on top of it? And the predicate will return true or false. And this describes the state of the world in terms of that Towers of Hanoi problem. We have an action operator, and this is really about what the action can do. In this particular problem, there's only one action, but in other problems, it might be more. It has three components. Component number one is the parameters, which basically says, my action operates on objects. Which objects do they affect? It has what is known as a precondition, which says, what is the state of the world that needs to occur for me to execute this action? So actions are not always executable. Sometimes you can only execute them under certain conditions. And so the precondition really says, when can I execute the action? And the effect is basically says, okay, well, if I can execute the action, here is how the world changes. And all of this is written in terms of our Boolean predicates to say, well, if I'm at this state where certain things are true, certain things are false, I can execute this action. And the effect is certain things get set to true and certain things get set to false. Okay, so this is what we want, the symbolic representation. But as we said, if we want a general purpose agent, well, it has necessarily high-dimensional sensors, like video cameras and so on and so forth. And it also has very low-level actions, like applying motor tools. So the question is, how do we go from that to a symbolic representation as we see on the top? And so basically what we're going to do is we're going to use machine learning to go from these low-level sensory data, low-level actions to acquire these predicates, to acquire these high-level actions or skills. So step one is really about acquiring skills. And it turns out that we don't need to worry about this too much because there's an entire subfield related to the idea of acquiring high-level skills. I've listed 4 or 5 there, but there are hundreds and hundreds of papers written about how to discover high-level useful skills. So we can just do that. We can just take one of their methods, apply it off the shelf, come up with a bunch of skills. So for instance, we might have like a little ant robot over here, and it might have skills that say, well, I want to walk to like the top two rooms. There's like little rooms over here. I want to walk to the center of the top two rooms, and it might have another skill for walking to the center of the two left rooms, for whatever reason. So we can discover these skills with a number of methods, and then we can just use those skills instead of relying on the low-level actions. Step 2 is then to say, okay, well, if we have the skills, how do we get those symbols? How do we get those predicates that describe the world? And one of the core ideas here is that the symbols that come out at the end really depend on what a robot can do, what the agent can do, right? Why is this the case? If you take a very simple example of like a wall with a door in it, if I'm a humanoid robot that has arms and legs and so on and so forth, well then, if I have the ability to open the door, my representation of this world should really be about representing the wall, which is like an impassable obstacle that I just can't walk through. And it should also be about representing the door because I can open and close that door. I have the ability to do that. So I want to represent the door in terms of, whether the door is open or closed. Now, on the other hand, if I'm a different kind of robot, like a Roomba or, one of these vacuum cleaners that's automated, I don't have arms anymore. And so, in this situation, because I can't open the door, there is no difference between the door and the wall. To me, those are just obstacles that I can't pass. And so the representation for the different agents will be different because they have different skills, they have different abilities. And so really the question of what are the correct symbols, what are the correct predicates depends on the skills, the actions that the agent has available to them. So that's the main idea here. And so, having said that, what we want is to say, okay, well, let's look at this action operator, which has preconditions, effects, and parameters. And so if we look at, say, the precondition, for instance, the precondition was a thing that said, if I have a skill, can I execute it in the current state? So this is saying, the agent, the robot is at a state. What is the probability that they can execute a given skill? And this problem is really just about binary classification. This is just saying, given a state, can I execute the skill, yes or no? And maybe there's, with some probability if things are noisy and uncertain. And so what we can just do is we can collect data of states where we could execute the skill. We can collect data of states where we couldn't execute the skill. And we just get that data and we apply machine learning. We apply any kind of binary classification method. And now we've learned a model that says, well, given a state, I can tell you if you can execute a particular skill, yes or no, and maybe with some probability. So preconditions are really just about classification. If we move on to the effect, well, what is the effect asking? The effect is asking, well, if I can execute the skill, what happens next? So I'm asking really, like, if I say what happens next, what I mean is, what is the distribution over next states, over future states that I could find, that the agent could find itself in? So this is really saying the distribution over the next states, given that you have just executed a skill. And this is really just about density estimation. So this is just saying we can collect some data where we have executed a skill. We now have a bunch of data where we found after executing the skill, the agent was in these particular states. And then we can put a distribution over that data. And now we have an estimate that says, this is what happens when you execute the skill. Okay, so basically the action operator we can derive just using some machine learning things, where one is classification, when can I execute the skill, the other is density estimation, which is what happens next. Okay, and basically there are some like bookkeeping details which are boring and I won't get into. But basically what this allows us to do is say, okay, well, we can learn a precondition, we can learn an effect, and then we can combine these two things to learn those symbolic representations. And so I'm just going to walk you through a quick example of doing this in a high-dimensional video game, which is called Minecraft. Minecraft is a very interesting and challenging benchmark because it is open world. There is no particular goal to it, and it is very high-dimensional, and there are thousands and thousands of different kinds of objects that all do different kinds of things. And the agent has free range to roam about, do whatever it wants. And so it's a good analog for the real world without having to use real robots that break down and cost money. So what we're going to do basically in the next little section is to say, given this high-dimensional video game, high-dimensional because the input is like pixels, and so your state space could be like 1080 by 720 by 3. That's a large state space. Given this, we're going to extract the objects from this game, and then we're going to do what we just mentioned, which is learn preconditions, learn effects, and build an abstract representation, which you can think of as a graph, but more generally is some factored representation. And then we can just give that graph to like a planet, come up with a plan to achieve some goal. And once we've learned the abstraction, the important thing is we don't have to go back to the game. Once we have the abstraction, we can throw the game away, we can throw all the high-dimensional data away, and just work with the abstract representation. Okay, so step 1 is really about extracting the objects. And fortunately, we don't really have to worry about this because computer vision, one of the main subfields of computer vision is about doing image segmentation, scene segmentation, saying if I have an image of a scene that has a bunch of objects in it, can I identify where the objects are? And there are many, many thousands of methods for doing this. So given an image, we can extract the objects from that image. And then we said, well, the next thing to do was, so just as an example, in the Minecraft domain, you might have something like this, where it's a bit hard to see with the contrast, but top left image is like a pickaxe, there's a bunch of doors, there's a bunch of blocks, there's an inventory, and so on and so forth. So we can extract these images from Minecraft itself. And then, as we mentioned, the next thing to do is really about acquiring some high-level skills. And again, we can use any off-the-shelf method that people have been working on to learn some skills. So here are just some short animations of different skills, like walking up to doors, opening doors, closing doors, picking up objects, using the pickaxe to smash objects, opening chests, things like that. So we can acquire all of these skills. And then having acquired the skills and the objects, we're then going to use machine learning to learn the preconditions and the effects. So in particular, what we're going to do is we're going to learn those symbols, those predicates that describe the world. We're going to learn the dynamics of the skills, which are just those action operators with preconditions and effects. In addition to all of this, what we're going to learn is what we'll call a type system. And the type system is very much like what you would see if you're doing like programming with object-oriented programming, where your variables might have associated types and you might have hierarchies of these. And the reason you want to do this is because it is useful for transfer. If we learn a representation that is parameterized by object types, then if we put the agent in a new environment or a new task, and we observe that there are objects of the same type, well, we don't have to relearn that because we already learned it in the first task. We can just reuse our knowledge. So we want to do this for transfer reasons, to make things more efficient. And then finally, what we get out at the end is a symbolic representation that is complete and sound that we can use to plan. Okay. And the reason we want to do this is because you can imagine what reinforcement learning at present does is it says, well, my observation is this image over here, where it's an agent standing in front of the door, and my observation is basically the individual pixels of this. And now, if you want to do something like planning, it's really hard to plan in pixel space because what you're saying is, well, if I execute an action, what is the next set of pixels that I see? Like, I have to predict every single next pixel that I see in order to do planning if I'm operating in this high-dimensional space. And that's obviously ridiculous to do because, for one thing, humans don't do that. Humans don't say, well, if I execute the action, then these are the pixels that we'll see. Humans say, well, if I execute the action, the door will open because I have some abstract concept of what it means for the door to be open, the door to be closed. And I don't care about the textures and the lighting conditions and so on. So it's very hard to do planning in pixel space for this reason. But if we had a representation like something on the right where it was symbolic and we were just saying there is a door and the door is closed, and if we execute the action, the door is open, well, that's just setting a Boolean variable from false to true, which is a very simple thing to do, and it's very easy to reason about what happens next. So that's the space we would like to be in because it's very easy to do forward planning, to think about the effects of your actions, and it's very hard to do that if you are in pixel space. Okay, so what we do is we run around, we collect a bunch of data by executing the skills, we do classification to learn the preconditions. In practice, it doesn't matter what classifier you use. For interest, we use a support vector machine with flat scaling to give us a probabilistic classifier. The details don't matter. It's really about, we want a classifier that says, given a state, can I execute the skill, yes or no? And then we do density estimation, which is, in this case, we use kernel density estimation, but again, you can use any density estimator that you want. Again, all of machine learning has been working on methods for doing classification, density estimation. You just use what you want. And you can use this to say, well, if I execute the skill, what's the next thing that happens? And then, you know, a bunch of bookkeeping later, we build a symbolic representation that we can use for that. But if we do this naively, what we find is that each object is treated individually. If we have 4 doors in the environment, we do this, and what we discover is that we treat each door separately. We treat each door as saying, well, I can open door 1, I can open door 2, door 3, door 4. So I get 4 operators that operate on the individual doors. And what that means is I have no opportunity for transfer. I can't use those representations elsewhere because my agent thinks that every single object is unique and there's no information to be shared. And so the next phase is really to say, okay, let's combine objects that are similar into similar object types. And how do we do this? Well, going back to the idea of saying the symbols that we need depend on the skills that you have. What we're going to do here is we're going to say 2 objects are similar if they admit similar actions. So if we execute a particular action on 2 objects, and the thing that happens to those objects is very similar, they look the same, then we're going to say that those 2 objects are the same. So what that means is that our types might be things like openable or closable or pickupable or things like that, and they depend on the actions that you have. So if the agent does not have an action to say open the door, then those doors won't be openable because the agent can't act on them, they can't open them. But basically the idea here is to say the object types that you have really depend on what you can do to them and what happens. Okay, so we can do something like that. So for instance, what we would then see is, initially having done this, what we learn is 2 separate things because we treat everything as independent. Door 1 and door 2 are completely different. But when we investigate these 2 things and we look at the effects, and here, you know, we can do this again automatically because the effects are just kernel density estimators. So we're just saying we have 2 distributions. Are those 2 distributions similar? So, you know, comparing 2 distributions for similarity, you could do something as simple as like a Kale divergence or any other kind of similarity. But whatever the case is, you're just saying, are the effects similar, yes or no? And if they are similar, then we're going to merge them together. And what comes out at the end is a representation that is parameterized by a particular type. And the preconditions and the effects operate on that type. So we have all of this, and that means that I can give this operator any door. If there are 10 doors or 100 doors or 1,000,000 doors, it knows what to do with those doors. It doesn't have to relearn it for every single one. And the result that you get is something that looks like this. And so on the left-hand side is kind of a visualization of what the symbols mean. But on the right is something that we actually learn directly from data, a symbolic representation. And this one in particular says something like, in order to open the chest, the agent must be standing in front of the chest, which is symbol 13. Symbol 4 says the chest must be closed. And P symbol 8 over there, which is basically the location of the agent. The P symbol is the one thing that you cannot transfer between tasks. Everything else you can transfer, so we can reuse a lot of knowledge. The red thing you would have to delete and relearn for every task, but everything else you can transfer. Basically, it says, you know, if you're standing in front of the chest and the chest is closed, the effect of that is that symbol 58 gets set to true, which means you're standing in front of the open chest. Symbol 59 is true, which is that the chest is open. And then you set symbol 4 and 13 to false to say, well, the chest is no longer closed. And so basically, we've just learned a representation that says, if you're in front of a chest, you open the chest, and the chest was initially closed, now the chest is open. And so what we can then do is we can throw all the high-dimensional data, we can throw out all the pixels, and we can just reason about things with the symbols. And basically, once you do that, then you can come up with a final plan. And you know, this plan over here that's being run has been discovered automatically. We discovered the symbols. We plan with the symbols alone. We throw away everything else. And so the plan is executed in the agent's head. He reasons about the plan in the agent's head in order to solve this task, which consists of like thousands and thousands of low-level actions. And it does this in its head. It doesn't have to worry about pixels or lighting conditions or high dimensionality or any noise or anything like that. It comes up with the plan and then executes the plan to success. Okay, and then finally, just a quick note, because we learned a representation that is transferable between tasks, what that means is as the agent sees more and more tasks, it can reuse more and more of the symbols and the action operators that it's seen before to solve the new tasks. So that means if I put the agent in a new task, it uses less samples to solve that task because it can just reuse past knowledge in order to solve it. Okay, so kind of just to wrap up and summarize, the idea here is that if you want really generally intelligent agents that are not just good at solving a narrow set of tasks, but can solve any task, then they necessarily need to learn their own representations. It cannot be that a human is required to specify an MVP or symbolic representation or anything else. We can't have humans in the loop. The agent must discover this from its own sensory data. In particular, one way of doing this is learning object-centric representations, which are useful for planning when there are objects, but of course doing things like autonomous self-driving cars will require other kinds of representations that we need agents to learn as well. And the last point was that we hopefully see this as a step towards more generally intelligent agents capable of acting in the real world.
Thank you.
Thanks.
So, Jared, I believe you have a question. Can you unmute and ask your question?
The formalism that you use for expressing actions works for sequential systems, systems with the actions in sequence, not in parallel. But actually, I think for general purpose AI or AGI, we really need parallel composition. So you need another way to formalize actions. What do you think about that? I think it's a hard problem. What do you think?
No, definitely. That's a great point. I definitely agree with that. I think one of the limitations of reinforcement learning and these kinds of approaches is that you're assuming like discrete time steps. So you're saying, the world is frozen. At a time step, I take an action, and then the world changes. But of course, that doesn't happen in the real world. We have continuous time. When we act, things are variable. There are dynamics that change that are outside of our control. I might do nothing and the world might still change because that is the way the world works. And so definitely I would say, that is an extremely difficult problem that I don't think we're even close to starting on. Like we can't even solve, we can't even get a handle on the discrete time. I'm the only agent that can change the world. So it's going to be very, very difficult to say, okay, well, the world can change by external factors and, we have continuous time and all the rest of that. So I think that's a super challenging, but also super interesting problem to think about. And one of the motivations, at least for this work, was to say, okay, well, let's bite off a small chunk of a class of problems where discrete symbolic representations are useful. And these are particularly useful when you're doing things like deliberative planning, where I can take my time. It doesn't matter how long it takes me to come up with an action or a sequence of or a plan. The world isn't going to change, so I can take my time. If I'm doing something like chess, if I take 1 second or 2 seconds, the chessboard remains the same, and so it's okay in that situation. But certainly these are not appropriate if you have real world cases of things changing. Again, like the self-driving car example, like this would never and can never work. It's not appropriate for that case, and so we definitely need different approaches and maybe even like a different base formalism compared to this agent environment loop where we say the agent takes an action, the environment returns an observation. That's probably not sufficient either in general. But yeah, a super interesting problem. I can't say I've given it much thought, but definitely something that hopefully others are working on.
Good. Thanks very much, Stephen.
Yeah.
Thank you, Jeff. Any more questions from a distance? Anyone here? Joey.
Stephen. So can you not leverage Markov chain type philosophy and also simulations?
Okay, so the question was about leveraging Markov chain philosophies and simulations. So absolutely. So the main idea here is really we want to learn so on one hand we're saying we have a high dimensional complex state space, and if we want to know what happens when you take an action, that's going to be impossible to predict into the future. So we can't do that. So what we instead need to do is learn a representation. In this case, that representation happened to be a symbolic representation, but that symbolic representation is equivalent to, say, a factored Markov decision process. And the factoring just makes things easier. It doesn't even have to be factored. It could just be a regular Markov decision process. But once we have applied machine learning and we've moved from a high dimensional space like pixels to a more abstract, say, MVP, we can then definitely do things like say, okay, well, I'm in the MVP let me throw away everything. Let me pretend I'm just in the MVP. Let me do simulations into the future to do Monte Carlo estimates of the value at my current state. So we want to be able to like say, I don't care about the high dimensional space anymore. I only care about this lower dimensional, but maybe still complex Markov decision process or whatever formalism you want to go with. And then we can apply different machine learning techniques in that case, which we also have to. We can't just say it's solved. We still need to apply the machine learning techniques there, like Monte Carlo estimates and all the rest of that. But that's where we want to be applying Monte Carlo estimates. We don't want to be saying, I'm going to do Markov chain Monte Carlo on pixels, because then it's going to take me 3 hours to predict the effect of just like a single action, which is not going to be useful for like things operating in real time in real.
You can extend Markov chains to continuous time. Beyond, I mean, I don't know how practical it is.
Yes.
In an application, but I mean,
yes,
you were talking a lot about discrete time. But
yes, absolutely. Yeah. So again, reinforcement learning in general, I think maybe the philosophy is it's hard enough as it is, and so let's stick with the discrete time formulation. But like the methods that you use for discrete time are really like derived from optimal control and continuous time methods like the Bellman equation and all the rest of that. And so it certainly can be applied. We just don't because it's hard enough as it is. But certainly interesting directions are to say, okay, we have all of this, but what about in the real world where there's continuous time? And some might say it doesn't matter. We can hack it if you have a fast enough hardware. We just have time steps that are like so short, it doesn't matter. It's fine. Let's not worry about that. But certainly it's an interesting direction to think about is, okay, what about continuous time? What about real world applications?
Epsilon 10 to 0 time.
Whenever I hear the word hack, I get worried. I'm sure you think of hack in a positive sense.
Not hack as in steal your data, more like hack as in there is a solution that is not theoretically sound that just happens to work.
Okay, so there is another version of the word.
Yes, still to be nervous about.
Yeah, of course. Okay, so if we don't have any more questions, thank you, Stephen, for the wonderful talk. And I hope none of the guys listening from a distance are going to steal you from bits. So stick around. Okay, otherwise we'll hunt it down to the Liam Neeson thing. Thank you very much, and let's give Stephen.